All right, so we've been talking in this unit about rational expressions and using them for different things. So we're going to just finish that up today with some final problems. The first page is we'll be able to review some of the stuff we've talked about, and then we will do some sort of applications, some simple applications on the other two pages. So here we go. What we're going to start with is something you're going to deal with as you go throughout some of your classes, maybe some science classes, or maybe economics or business class, if that's going to be the route that you take. You're going to have to learn to manipulate formulas or be comfortable using formulas in some capacity. So we're just going to practice a little bit with that here. Formulas are just equations that have some extra unknowns and being able to rearrange them. So the first thing we're going to do is we're going to be given a formula. We're going to have some values given to us, and then we have to find the missing values. So for instance, in example 1, got this equation right here. If you were in optics, if you were making pairs of glasses, this is an equation from optics. Not that that matters one way or the other, but this is an actual thing. So we have 1 over f equals 1 over p plus 1 over q. We're going to find the value for q if I know that p is 20 and f is 10. So we're going to go through and do a little plug and chug here. So I'm told that f is 10. I'm told that p is 20. So first thing I'm going to do is I'm going to put the appropriate value in the appropriate place. So instead of 1 over f, we're going to have 1 over 10. And then we're told that p is 20. So instead of 1 over p, I'm going to have 1 over 20. And then q is what we're looking for. So 1 over q. This is a good little review problem for us because this is just what we did in the previous section, section 6.4, where we solved equations. And we solved equations by clearing the fractions so that I wouldn't have any anymore. So what is my common denominator among 10 and 20 and q that I'm going to multiply everything by? Not those of you saying 10, remember, here's the check. If I was to multiply everything by 10q, it would get rid of this first fraction for sure. But then here, the second fraction, 10 would not fully cancel out the 20 in the denominator. So that would not be enough. So you'd have to go back to the drawing board. So then those of you who corrected, or maybe it was your first impulse who said 20q, that is going to be the appropriate common denominator. So I'm going to multiply each of my fractions by 20q. Remember to find that coefficient. The easiest, quickest way I can show you is the listing method. So you list out the multiples of 10, you list out the multiples of 20 until you find the first one that they have in common, which in this case is 20. All right, so now canceling. 10 goes into 20 and leaves me 2. So what we have is 2 times q equals 20 goes into 20 and just leaves q. And then last but not least, on the third fraction, the q's cancel, and I just have 20. So we have 2q is equal to q plus 20. No more fractions. That's the goal. We feel a whole lot better about the problem. And I'm just about done solving. I'm going to subtract the q from both sides. 2q minus q is equal to q. And so we get that q is equal to 20. Okay, there we go. Done with the problem. So you have a very similar problem in exercise 1. You're going to use that same formula, 1 over f equals 1 over p plus 1 over q. I've changed the values. P is 50, q is 10. You're going to find the value of f in that case. So first thing I'm gonna do is I'm gonna plug in the appropriate value in the appropriate place. So we're looking for f, so that first fraction is going to stay 1 over f. There's no change to make there. Equals, and then 1 over p is the next fraction. So p is 50, so that's 1 over 50. And then plus 1 over q, and I'm told q is 10, so that's 1 over 10. So there is my new equation. I don't know what f is, so I am going to go ahead now and clear the fractions like we've been doing. What is my common denominator between f and 50 and 10? 50f, yep, 50f. So we multiply everything by that 50f. The first fraction, the f's cancel, and I just have 50, great. The second fraction, the 50s cancel, and I've got 1f or f. And then the last fraction, 10 goes into 55 times, and I have 5f. So we get rid of the fractions. We have 50 is equal to f plus 5f. Again, it looks a lot nicer because the lack of fractions, and this is something we've been used to dealing with since the beginning of the semester. So I have 50 is equal to f plus 5f, that's 6 of them. Just going to take this equation right here. I'm going to write it up where I've got some white space up here to be able to go ahead and write. And then last thing I'm going to do is divide both sides by 6. And we get that the value for f that we have here is 50 over 6, which reduces by a factor of 2. 2 goes into 50 25 times, and 2 goes into 6 3 times. And so I get 25 over 3. That's the value that creates my equals. So that was a new skill, gave us opportunity to review solving. Any questions so far? All right, what we're going to do next is something a little bit more common, though. So now example 2, we're going to take that same equation, and now instead of plugging in values, what we're going to do is we're going to solve for p. Meaning, I'm going to write this equation in a new format that says p equals something. Okay, maybe I'm always going to know what f and q are, and I just want this to be a straight shot when I plug values in. So we are going to solve this for p. Well, before I worry about solving for p, I'm going to do the same thing here that we just did in the previous problem, and I am going to clear the fractions. So let me rewrite my equation. I've got 1 over f equals 1 over p plus 1 over q. If I'm going to clear the fractions, what do you suppose is going to be the common denominator that I have here? F, P, and Q, one of everything you see, F, P, and Q. So the least common denominator is F, P, and Q. Doesn't matter what order you put those letters in. I'm just in alphabetical there, but it doesn't make any difference. So I'm going to multiply every one of these terms by F, P, Q. So F, P, Q here. And then we're going to squeeze it in right there, FPQ, and then FPQ right there. So this is going to give us an equation that doesn't have any fractions. It's going to be more palatable to us, a little easier to look at. So the first fraction, the f's cancel, and I have p times q. The second fraction, when I cancel the p's, what's left there? Sure, f times q. And then the last one, the q's cancel, and I'm just left with f times p. All right, so here's where we're solving a equation rather than, we're solving a formula rather than a equation where we're going to come up with a value. So here's the part where we just have to pay a little bit of attention. What is the letter that I asked in the beginning to solve for? We're solving for what letter? P. So what that means when you're solving for the letter P or whatever it would have to be, you have to get every term with that letter on the same side. Okay. So I've already got the P and the Q. They're there. Is there another term on the right side of this that has a P in it? Yeah, this last one right here, the F times P. So what I'm going to do is I'm going to get that over to this side. So let me just make a little note for you. When you're asked to solve for a variable, you have to get every term with that variable on the same side. Okay. So get every term with the P on the same side. Now, sometimes there's only going to be one term with the letter you're solving for, but this time there was two. So what that means is I'm going to subtract f times p. Are these two things like terms? P times q minus f times p? No, they're different. So I can't smush them together. So I'm going to leave them separate. I'm going to have p times q minus f times p is equal to, on the other side, I have a term that has no letter p in it. So because I have two terms with a p in it, and I can't smush those together to make one thing. I mean, because like in exercise 1, when we solved this, we had f plus 5f. We were able to smush those together. They were like terms, so I was able to put those together. So I just had one term and I could divide. Unfortunately, I can't do that here. So what I have to do in this instance right here is I need to factor out that p that they have in common. So I'm going to factor out the p. Probably the hardest step of the problem. So if you have a question about it, if you're having trouble visualizing it, let me know. I've got to factor that out. When I have PQ and I factor out the P, I have Q left. When I have FP, I factor out the P, I've got F left. And now I got one more step. Once you've done that, that's the hard step to remember to do. Once you do that, I'm going to divide by that thing right there. And here's what we get. We get P. I've solved it for P. Now my equation says P equals, and then I have F times Q on one side and Q minus F on the other side, and we're done with the problem. So that's a little bit of a difficult thing, and I understand remembering to get everything with the variable you're solving on one side, that can be a tricky thing. So exercise 2 is going to present you a similar situation. I've changed the letters a little bit, made the equation a little bit simpler. So go ahead and see what you can do. You're solving the next one for M, that letter M. What's the common denominator that you're using on that first step? Yep, M times N, perfect. All right, let's see how you did here. M times N is the common denominator, so we're going to go through. So the first term, M times N times 1 over M, the M's cancel, and I'm left with N. So there's my new first term with no fraction. minus, and then the second one, I've got m times n times 2 over n. The n's are going to cancel here, and so I have 2 times m as the second one. And then on the other side, there's no fraction to cancel, so I have 5 times m times n. So if you did that first step, you're doing great. That's what we've already done in this class, the last class period. So you're spot on. Now this next part, this is the new part. I'm solving a formula versus just a plain old equation. I'm solving for m, so I got to make sure that all the terms that have an m with it are on the same side. So what do I need to move here? Yeah, I need to move the 2m to get everything with an m on the same side of the equation. So I'm going to add that 2m. And again, these are not like terms. The 5mn, that has an n in it. The next one, 2m, does not. So they're not the same. You can't smush them together and get 7 of something. So I've got to keep them separate. So on the left, I've just got n. On the right, I've got 5mn plus 2m. And once you've done that, once you remember to get everything with the same variable on the same side, now it just becomes factor out that variable you're solving for and divide. So both of these have an m in it, so I'm going to factor that out. 5mn, when I factor the m out, I have 5n. 2m, when I factor the m out, I have 2. And so when I divide, here's what I have. I'm just going to write it off on the side right here. I've got m equals n divided by 5n plus 2. So just rearrange the same thing, rearrange the factors into a new equation that if whatever application you're doing this in might be a little bit easier to use than the original thing. All right, one more time, just to practice this concept once more. Exercise 3, you're solving for the capital N. If you're not aware of this, when you work with formulas, there is a difference between uppercase and lowercase letters. Okay, so like if you're in a natural science class and you're looking at the gravitational pull formula, there would be a capital M for the mass of the larger object and a lowercase m for the mass of the smaller object. So anyway, this happens sometimes. So I just mention all that because you've got 2 different n's in the denominator of this. So we are solving for the capital N. What's the common denominator of this problem? Yeah, it's the only denominator, the capital N minus the little n. So I'm going to write that down. Keep working. Okay, so when I multiply by the n minus n on the left, that cancels, so that's nice. And I'm left with capital N times R. And then on the right, I'm going to distribute because there's no fraction to cancel. So I have capital N times T minus lowercase n times T. If you have the order of the letters different, that's fine. I default to alphabetical order, but it's not mandatory. So again, we are solving for the capital N, so I have to make sure that every term that has a capital N is on the same side of the equation. So that means what term do I need to move to the other side? Yeah, the capital N times T. So I'm going to move that. So on the left, once again, these are not like terms. That's the added difficulty with solving a formula rather than a regular equation like we've been doing. So that is going to be capital N times R minus capital N times T. And on the other side, I have negative N times T. Again, that's the hard part to the problem. That's why I've had you do this a couple times, is so that we get the opportunity to practice. The rest of this, I'm going to factor and divide, and we'll be done. So that now that I have everything with that capital N on the same side, I can factor it out. And when I factor that out, capital N times R, I factor out the capital N. I've just got R left minus capital N times T. When I factor out the N, there is the T. And I have the negative little n times t on the other side. And then the last step, last but not least, we are solving for the capital N. So I have to divide by this factor that is in the parentheses. And so here is my final answer at long last. The capital N is equal to negative little n times t. And then in the denominator, capital R minus t. All right, so that was just a brief little soiree there into manipulating formulas. That's the first of the tasks that awaits you on these last couple of quick sections that we have at the end of chapter 6. The next thing we're going to do involving fractions is going to be solving what's called a proportion problem. A proportion is just a ratio, and what we're going to do is we're going to set two ratios equal to each other, two comparisons equal to each other. So, for instance, there are other ways you could do example 3, but I'm going to intentionally do this using a proportion because you're going to then replicate the process on the next few problems. So, it says at a gas station, if I buy 3 gallons of gas, that's going to cost me $12.27. So if I don't know anything else about the problem, how much would 13 gallons of the same gas cost? So we're going to set this up as a proportion so that we can solve it. So when we set up a proportion, what we're going to do is we're going to take the first comparison. We're going to take this 3 gallons of gas for $12.27, and we're going to make a ratio out of it. And so I'm going to say, okay, 3 gallons over $12.27. Hey, Perkster, what if I had already been writing down the problem and I wrote it, if I flip that fraction? So maybe you would say, I would have written it 1227 over 3 gallons. Well, that's wonderful. Okay, you just have to remember to do something different on the second proportion, on the second fraction. I'll show you that in a minute. Okay, so I've written this as 3 gallons is 1227. And then it says, okay, how much would 13 gallons of the same gas cost? So I've got 13 gallons. According to the way I've set up this problem in pink right here, where do you think I'm going to put the 13 gallons in my fraction? On the top. Yeah, that's the only thing you have to remember when you're setting up your proportion, is like units have to go in the same part of the fraction. So since I put my gallons on top on the left side, I got to put my gallons on top on the right side. And then the denominator is the thing I don't know. That's the how much is it going to cost. We'll come back and solve that in a minute. But just in case your impetus would have been to write the ratio as 1227 over 3 gallons, that is perfectly wonderful. You just have to remember, where are you, if you did it like this, the green problem, where are you going to put your 13 gallons? In the bottom, yeah. You're going to come up with the same answer either way. It actually, neither one of these is righter or wronger than the other. They're equivalent. Okay, so then we'll put the X up there. Now, because of clearing the fractions, if we were going to solve this, we'd clear the fractions. Here's the shortcut, okay, that results. This is the pattern that somebody along the way noticed when you go and clear the fractions on a proportion. Since I have just one fraction on each side, what we can do is we can solve this by doing what's called multiplying along the diagonals. So what I mean by that, in case that's a little confusing to you, is I'm going to multiply along these diagonals. I'm going to make a big X right there. And this just results if I was to go ahead and clear the fractions. So this is just a shortcut to the same place. So what I've got is I've got the 3 gallons times X, so that's 3X. And then on the other side, I have the 1227 times 13. Okay, this works because we're solving an equation. We're not multiplying the fractions together. We're solving an equation. So here's my calculator. I've got the 13 times the 1227. And that turns out to be 159.51. And now, end of this is I'm going to divide by 3 on both sides, and I get that the amount of 13 gallons of this gas is $53.17. And that's solving a proportion. I'm guessing probably at some point you've seen that and solved a proportion in some math class along the way, but just in case you haven't, the setup's pretty straightforward. Just remember, again, just reiterating, just remember to put the same units on the same part of the fraction. Once you've done that, you're going to be golden solving these problems. So exercise 4, I know that we don't really use maps much these days. I should change these examples, but we're going to go ahead and use proportion to solve exercise 4. So what it says is on a map, the distance between Reno and Phoenix is 2.5 inches. The two cities are really 768 miles apart. So there's a relationship that we know right there. The map distance versus the real distance. So then on the same map, what would the distance between Chicago and El Paso be if they are really 1,606 miles apart? So set that up, solve it, and we'll compare notes in just a minute. All right, so let's see how you did on this first one, and then we got 2 more that are going to be just like it, so we can work out any issues that we might be having. So the first relationship I know is that 2.5 inches is the same thing as 768 miles. Again, I'm not going to write it down, but if you wrote the 768 miles in the top and the 2.5 inches in the bottom, that is great. Don't erase it. Don't cross it out. Keep going. But whatever you did, I now know that these other two cities are 1,606 miles apart. Where's that going to go on my ratio right here? On the bottom, yeah. And so if you had put the miles in the top, then you put the 1,606 in the top. Just be consistent. And then I want to figure out what's the map distance. So that's the X. I don't know what that is. So the shortcut to solve this is I'm going to multiply along the diagonals right here. So there's my X that I'm going to do. So 768 times X is 768X. And then 2.5 times 1606. So 2.5 times 1606 is equal to 4,015. And then I'm going to divide. And we get X, this map distance that I'm looking for is 4,015 divided by 768. And boom, it's going to be 5. We're just going to round to 1 decimal place because that's what the other map distance was. So it's just going to be 5.2 inches when I round appropriately. 5.2 inches. Anybody got a question about solving a proportion problem? All right, then do the next one. It's a similar problem, just a globe this time instead of a map. And then we'll have a new problem, a projection problem. Okay, so the first relationship I know is that the actual distance between New York and Cairo is 5,619 miles. And on the globe, that is represented by 8.5 inches. Okay, so I've chosen to put the miles in the top, the inches in the bottom. If you did the reverse, that's fine. It's going to work out the same. On the same globe, I want to know how far apart are Madrid and Rio de Janeiro if they are actually 5,045 miles apart. So since my miles are in the top, I put those in the top, and I don't know what that globe distance is. Just be consistent. That is the biggest takeaway for you when setting up a proportion problem. Now I will multiply along the diagonals here to solve this. This is my shortcut to do it. So 5,619 times X. And then I've got 8.5 times 5,045. Sure, you've used your calculator and you got 428,000. Oh no, sorry, 42,882.5. Didn't see that decimal point at first. And then we divide. And we get that x is going to be equal to, and again, I'm just going to round to 1 decimal place because the other distance was 1 decimal place. So that is 7.6 is going to be the number of inches on that globe. Doing okay? All right, one more. Proportions are used a lot. One of the common applications, I'm guessing maybe even outside of like a classroom, you would use it, is to make projections. So this is a sports projection right here. So this is an older statistic, but at one point the Indiana Pacers had won 48 of 65 games. If they kept winning at the same rate, how many games would they have won in an 82 game season? So you're going to set up your proportion and then solve it, and then we'll answer the question, see how it goes. Right, so first, the relationship that I know is they won 48 games. So we've got 48 wins out of 65 total games. And I want to project that into the future. If they kept doing the same thing, how many games would they win? So I don't know how many wins out of 82 total games in the NBA season. But that's what that looks like. So we'll multiply along the diagonals one more time like this. And so the first diagonal, 65 times x, is 65x. The next one is 48 times 82. That gives me 3,936. And then we'll divide. And we get x is equal to, so the exact answer is 60.55 or 60.6. But if we're going to answer the question, okay, you can't win 0.6 of a game, so we're just going to round that appropriately. So we're just going to say, okay, that would be 61 wins. So the difference between this problem, the reason I put this one on here is the difference between this one and the previous two. The previous two, you can have a part of an inch. Okay, that's why we left those decimals. Here, you can't have part of a win. So wins are whole numbers, so we just rounded appropriately to 61. All right, one more thing. So the first thing we did today is we talked about formulas and manipulating those a little bit. Then we talked about specific proportion problems. That's a super, it's a super applicable skill that I'm thinking you'll probably use a little bit. And then the last thing is we're just going to talk about a couple of relationship words that you'll see. This is kind of tucked into this chapter right here. So we're going to talk about what's called direct and indirect variation. Okay, so first, I'm just going to define the words that you're going to see, and then I've just got a couple problems for each. So the first one, direct variation. If you see something like this, I'm just going to write this above the problem. If you see something like this, y varies directly as x, or whatever the letters are going to be. Y varies directly as x. then as an equation, what that means is that y and x are moving in the same direction. If y is getting larger, then that means x is getting larger. They are in direct relationship. If y is getting smaller, x is getting smaller. And the way you express this mathematically is you'll say y is equal to some constant. So we just represent the constant by the letter k. Okay, so this is the variation constant. Times x. And that's how to represent a direct variation or a direct proportion. We'll come to the second one in a minute, but let's go ahead and work a problem and get used to the process. And then I'll tell you what, it actually shouldn't be indirect variation. This should say inverse variation. Sorry, that's bad typing by me. But we'll get to that in a minute. So example 4 is my example of this. It says that Hooke's law for a spring states that the distance d that a spring will stretch is directly proportional. The key word here is directly. It's directly related to the force F. So I'm going to stop. I'm not going to read the second sentence just yet. What we're going to do first is we are going to translate that into my relationship. It says the distance d that the spring stretches is directly related to the force F. So that means D equals K times F. There's the direct relationship. You're going to get your chance to do this same thing in a minute because exercise 7 is another direct relationship. And so you're going to take the first sentence, you're going to write the very generic equation, and then we'll go back and do some numbers. So here's my second sentence. It says, if a force of 150 newtons, a newton is just in physics, it's how you measure force of things, how much you're pushing or pulling. You don't need to know that. I'm just giving you that context. So if a force of 150 newtons stretches a spring 8 centimeters, find the value of K. Okay. So we just have performed an experiment. We've gotten to know this spring that is hanging from a hook in our lab. And we know that if we put 150 newtons on this spring, it stretches 8 centimeters. Okay, so what am I going to substitute for D? 8. 8 is the distance, so 8. K, I don't know. I'm trying to figure out how this spring operates. But once I do figure out K, it won't change for this particular spring anymore. And so that gives me a known fact. So I have K times, and then the value of F, the force, is 150. I'm going to divide both sides of that by 150. Not a whole lot to solve here. And I've got K is equal to, I can reduce that. It looks like 2 is going to go into 8 4 times. 2 is going to go into 150 75 times, and that can't be reduced anymore. So there is my value of K, the spring constant. Well, then I'm asked now to make a projection. Okay, how much then do I anticipate a force of 400 newtons stretching the spring? So I've got this equation. I've got D is equal to K times F. This time I don't know what the distance is. I don't have a 400 Newton force, so I'm just going to use my new equation. So D is equal to, I've got 4 over 75 times 400. This just becomes a calculator problem. So I've got 4 over 75 times 400. So that is going to be 4 divided by 75, and then I'm going to multiply that by 400, and I get 21.333333. So we'll just round that to 21.3 inches. So exercise 7, this next one, I'm going to just ask you to do the same thing. It's a slightly different situation. Don't worry about this this sentence down here. We'll do that in a second. Just do what the first paragraph says. This time we're not stretching a spring, we're compressing it. So pay attention to the letters and as you set up your equation. All right, so let's see how you're doing and ask me any questions that you need to. So this one says the force F required to compress a spring is again directly proportional, directly related. So it's the same thing we just did on the previous problem. So the force required to compress a spring is directly proportional to the change in length L of the spring. So I'm going to stop and I'm going to translate this into my equation based on the fact that the relationship is a direct relationship. So that means the force F is directly related to the length. So that is K times the length, L. Now I'm going to be given a relationship so I can figure out the constant. So if a force of 20 compresses the spring 2 centimeters, find the value of K. So the force is 20, and the compression is 2. Divide. 20 divided by 2 is 10. So K is 10. Just going to pause because I heard a couple people erasing. And so I don't know what the mistake you made is. But let me just mention, if you inverted the relationship. So for instance, on this, I'm not going to do the whole problem this way. But if you had written down the length is Ka times the force, your K will be different, but you're doing the same problem. You've just flip-flopped the variables, and that'll be fine. You'll come up with the same answer eventually. So if that's what you did and you were erasing, you can go with it. That will not lead to a wrong answer on the problem. Okay, so just wanted to make note of that. So my value of K is 10. If you did the problem this way, then your value of K is going to be 1 over 10 because you did it the variables in the reverse order. Nothing wrong with that, because now that I know what the value of K is, the next part says how much force is required to compress the spring 12. So I'm going to write down F is equal to K times L again. And so I want to know how much force. So I don't know what F is. I do know that K is 10 and then L is 12. And so that is going to be 10 times 12 is 120. And then I'm just looking up here in the problem. The units are newtons. So I'm just going to write that down as my units. But now that we know K and now we know the equation, whatever value of K, whatever way you had the equation formulated, it's going to work out. Answer this sub question right here. Okay, we're using the same spring. A force of 50 newtons would compress the spring how much? So this is just a plug and chug now. This time, instead of not knowing the force, I do know the force. So it says a force of 50. So I've got a force of 50. K from the previous problem is 10. And then I want to know what the length is going to be. So now when I divide both sides here by 10, I get that the length L is going to be 5 centimeters are the units that we used right there. All right, so we're just about done for the day. Got any questions? Anything you need me to follow up on? That'd be great. So varies directly means that if y varies directly as x, that means y is equal to k times x. They're doing the same thing. If y gets bigger, x gets bigger. If y gets smaller, x gets smaller. That's what a direct relationship is. The other type of relationship that we're going to do in this course, there's other ones, but these are the main two that you see most frequently, is y varies inversely as x. Okay, an inverse relationship. So practically what an inverse relationship means is they're doing the opposite thing. So if y is getting bigger, then x is getting smaller. And if y is getting smaller, x is getting bigger. They are going in opposite directions now. And so mathematically, the way we express that relationship is y equals k, but now instead of times x, it's divided by x. And that's why our book sticks this topic in this chapter, is because of these fractions that we get in an inverse relationship. So exercise 8, we're going to take in 3 phases, just because I've only got the one exercise for you to do. Here's what I would like you to do. For the first sentence, it says the current C in an electric circuit varies inversely as the resistance R. I want you to set up the very generic equation first, like we did on the previous problems. It's an inverse relationship. Okay, so if the current C varies inversely as the resistance R, the equation I'm going to do is C is equal to K divided by R. If you wrote down R is equal to K divided by C, that will work out too. Okay, so keep going with it. So next thing I would like you to do is you are given a known relationship to figure out the constant. So if the current is 20 amps, when the resistance is 5 ohms, find the value of K. So go ahead and do the arithmetic on that. Okay, so substituting the numbers, it says the current is 20 amps, so the C is 20. And then the resistance is 5 ohms, so the R is 5. So I get 20 is equal to K over 5. And then to solve that, that's just it's just a fractional equation. I'm just going to go ahead and multiply both sides by the common denominator, which is 5. And when I do that, 5 times 20 is equal to 100. And then on the other side, the 5s cancel, and then we get K is equal to 100. So the last thing then that we're going to do is, now that you know the value of the constant for this circuit, what is going to be the current when the resistance is 7.5 ohms? So figure out that last thing, and we will be done with this section. So again, plugging and chugging, I don't know what the current is, so C is still C. I do now know that K is 100 for this particular circuit, and then the resistance is 7.5. And when I pop that into my calculator, 100 divided by 7.5 is going to be 13.333333. So I'm just going to round that to 13.3, and the units on current are amps. So we'll write that down.